Hi everyone. So today my topic is introduction to complex numbers. According to the syllabus content, complex numbers is in year 12, extension 2. So today in my lesson, I'm going to cover two main points. The first one is use the complex number system. And the second one is represent and use complex numbers in Cartesian form. So in use the complex number system, it includes develop an understanding of the classification of numbers and their associated properties, symbols, and representations. It also includes define the number I as a root of equation, x squared equals to -1, and also use the symbol I to solve quadratic equations that do not have real roots. And in represent and use complex numbers in Cartesian form, students need to learn how to use complex numbers in the form z equals to a plus bi, and also define and perform complex number addition and subtraction. I will not include multiplication and division in today's lesson. So complex numbers, why is it important? Because it opens a new world of mathematics. Complex number system has a great importance in the field of mathematical physics. Also, a lot of real world technology and applications are based on complex numbers. Complex number systems provide methods and answers to problems that were once thought impossible. It also refines the understanding of the relationship between the extension of the real number system, geometry, and algebra. In addition, complex number systems enable exploration of how different math representations inform each other, like Cartesian form, polar form, and so on. So students might struggle in converting and understanding the relationship between the Cartesian, polar, and Euler form of complex numbers. Also, some students cannot fully conceptually comprehend the differences between complex numbers, real and imaginary numbers. Students can be confused on the terminologies of like imaginary and complex. Students can be confused because they might think imaginary means make up or not real. So complex must means the opposite, like solid and real, which is incorrect. Students might have difficulties in connecting algebraic and geometrical representation of complex numbers as well. They might struggle to connect the symbolic and geometrical representation. So this is because students were actually not introduced to the graphical or geometrical representation early in their study of complex numbers, and they were only introduced to it when they had to change the Cartesian form to like the polar form. So the teaching approach I'm going to use, firstly, I'm going to explain to students what complex numbers and imaginary numbers are, and justify to them why they are matter in mathematics by connecting them to the development of numbers and algebra. I'm also going to use videos and a lot of diagrams to illustrate the complex numbers. Okay, now let's start our teaching. So I want to introduce complex numbers systems from the development of numbers. We know that numbers starts from counting. So initially we have natural numbers like 1, 2, 3, 4, and so on, right? But then we realized that these natural numbers or counting numbers are not enough for us to describe situations, such as a whole number of people or groups that you want to separate them out or to share them into. So new numbers have to be introduced, right? And that's how we have like rational numbers, such as fractions, like 1/2, 1/3, a quarter, and so on. And also, for example, in trigonometry, even though we have like whole number like length, like 3 and 5 here, but what we get in hypotenuse is a totally different kind of number again. So that is 9 plus 25 is square root 34. So it is not integer or rational. What is it? And square root 34 is called a irrational number. And so this irrational number, so now the irrational number has to be introduced in this case. So you see how numbers are developed in math history. Everyone starts from the counting numbers 1, 2, 3, and 4. But when you start to combine this in different ways, you start to realize 1, 2, 3, and 4, they are not enough, right? So to think about this systematically, what binds these ideas all together is that we manipulate them through the laws and operations of algebra. So if we combine them with plus, minus, times, divide, and indices, these 5 algebraic operations, you will see all of these different kinds of numbers they pull out. So for instance, let's say x minus 5 equals to 0. And the solution for this is x equals to 5. And we call it 5 as a natural number and represent it by the letter n, right? And then we can record our solution on the number line here. And also, let's say x minus 2 equals to x plus 2 equals to 0. And the solution for x plus 2 equals to 0 is x equals to minus 2. And minus 2 is an integer. And we use the letter z to represent integer. So x equals to minus 2 is here. And what about 2x minus 1 equal to 0? The solution for 2x minus 1 equal to 0 is x equals to 1 over 2. And 1 over 2 is a fraction, so it is a rational number, but we use the letter q to represent rational number, which is called quotient. And we also have x squared minus 5 equal to 0. And what is the solution for that? So x equals to plus and minus root 5. And plus and minus root 5, it is irrational number, but we use the letter r to represent it. So r for real number. So they are real numbers. Right? But there's one missing. So what kind of equation could I craft that would get me out of not only the natural numbers, not only the integers, not only the quotients, and not only the real numbers? So how about x squared plus 1 equal to 0? What is the solution for that? So the solution for x squared plus 1 equal to 0 is x equals to plus and minus square root of -1, right? And square root of -1, if we see it on this number line, right? Square root of -1 is not between any numbers that we know up here. So it does not exist in the normal dimensions we usually know. So it does not have real solutions. And we call this an imaginary number indicated by the letter I. So I represents square root -1. So now we can also write x equals to plus and minus I. And we call this x equals to plus and minus I, we call them complex numbers represented by the letter C. So the graph here clearly illustrates like the inclusions of different kinds of numbers. Okay, now let's show this equation on a graph, x squared plus 1 equals to 0 on a graph. So we know that y equals to x squared plus 1 is this parabola, right? So x squared plus 1 equals to 0. It does not have solution, right? Because there's no intersections between this parabola and x-axis, but does not have real solutions. Doesn't mean it doesn't have solutions. It can have complex solutions. So if we extend our number system, we can actually find an answer to this problem. So I want to show you a simulation.
Square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full two-dimensional form, we can see how our function x squared plus 1 really behaves.
Okay, so in this simulation, right here, we see that they added this new number system and turn out this parabola actually crosses the x-axis, right? So what are these new numbers? Please don't be fooled by the name. Just because it is called imaginary doesn't mean it does not exist. It does exist, but it exists not in the real number line that we usually have. And what actually happens to this real number line is not going to be changed. It's not going to be changed. into two-dimensional. So we are now going to have an extra dimension, which is going to be our imaginary numbers. We have a new dimension called imaginary. So we are now going to have an extra dimension, which is going to be our imaginary numbers. So this includes our, so we have the solutions for this one. The solutions for this is x equals to plus and minus square root of -1 or plus and minus I, right? So now we can include our complex number solutions, plus and minus square root of -1 onto this graph here. So square root of -1 minus, right? So x equals to plus I and x equals to minus I. So imaginary number equals to real number multiplied by imaginary unit I. Now let's see another example. So x squared plus 9 equals to 0. So x squared equals to -9 and x equals to plus and minus square root -9 equals to plus and minus 9 equals to 3 squared, so equals to 3 times square root of -1 equals to plus and minus 3i, right? We can plot this onto our graph, imaginary and real graph. So x equals to plus and minus 3i. That's 3i. That's minus 3i, right? Okay, let's see another example. Here, x squared minus 4x plus 13 equals to 0. We need to use our formula. X equals to 2a for -b plus minus square root b squared minus 4ac over 2a. So x equals to b squared is 16 minus 4 times 13. And x equals to 2, -36. Equals to 6 squared. So 6 times square root -1 equals to 2 plus and minus 3 square root of -1 equals to 2 plus minus 3i, right? And we can plot this onto our graph. So 2 plus 3i is here, right? 2 plus 3i and 2 minus 3i is here. This 2 minus 3i. Okay, so complex numbers and solutions contain two parts. So please write this down. So complex numbers or solutions contain two parts. The real component plus and the imaginary component. So for example 2, our answer is x equals to, let's say 2 plus 3i. So what is the real component in this solution? The real component is 2, right? This is the real component. And what is the imaginary component? The imaginary component is 3i, right? So here is the imaginary component. And let's see our solution for example 1. X equals to, let's say x equals to 3i. What is the real component of x equals to 3i? Does it have a real component? So it doesn't have a real component, right? So the real component real component equals to 0. And it only has a imaginary component. So imaginary component equals to 3i. Yeah. Okay, now let's move on to adding and subtracting complex numbers. So let's have a look at the example 1. So we add their real components together and then add their imaginary components together. Okay. So let's say example 1 is 1 plus 4i plus 2 minus 3i. Let's say 1 plus 4i is complex number A, and 2 minus 3i is complex number B. So we add their real components together. So that is 1 plus 2. And we add their imaginary components together. So the imaginary component for complex number A is 4i. And the imaginary component for complex number B is minus 3i. So 4i minus 3i. So 1 plus 2 is 3. 4i minus 3i is 4 minus 3 is 1. So it's 3 plus I. Now let's illustrate this addition on a real imaginary graph. We can draw a vector from the orange for A and also draw a vector for B. So A1 plus 4i should be here, right? This is A. And for B, 2 minus 3i should be here. 2 minus 3i, yeah. And because it is A plus B, so we moving or panning it from the orange and match the tail of B to the tip of A without changing anything else. Don't change its bearing and magnitude. Like that. So we can see the new vector A plus B is here. So this is A plus B. And A plus B is 3 plus I. So which is the same as our answer, right? 3 plus I, 3 plus I. So that is how we add complex numbers and how we represent it geometrically. Now and example 2 is about the subtraction of the complex numbers. And we do the same. We subtract their real components together, and then we subtract their imaginary components together, okay? So let's say 2 plus 5i is the complex number A, and negative 4 plus 2i is the complex number B. So we put their real components together. So 2 minus 4. And then we put, oh, sorry. So we firstly subtract their real components together, right? So 2 minus 4. And then we subtract their imaginary components. So 5i minus 2i. So 2 minus negative 4 is 6. And 5i minus 2i is 3i. Okay, now let's illustrate this subtraction on this graph. So let's firstly draw the vectors for A and B. So 2 plus 5i should be here, right? That's for vector A. And minus 4 plus 2i should be here. This is B, right? This is B, but A minus B. So the minus of B is like the opposite of this B, right? We don't need to change its magnitude. We just need to change it, like flip its directions, like 180 degrees. So this dot line here should be minus B. And A minus B, we just need to pan it from the orange and match the tail of minus B to the tip of A. sorry. I will just use another color. So I will use red color for this. Okay. So our answer for A minus B should be here. A minus B. And this equals to 6, 1, 2, 3, 4, 5, 6 plus 3i. 6 plus 3i, so which is the same as our answer. Okay, so that is my lesson today for the introduction of complex numbers. And I hope you enjoyed it.